welcome back. Now we're starting to cover some new material for today, and right here at the very beginning I just want to call your attention to that fun article that I sent to you about with regard to Richardson. And Richardson is really one of the great crazy people in the history of meteorology, and I thought it would be useful for you to get a sense of kind of the cool thing about who invented models. You know, all these numerical models of weather and climate. It's a little bit of a stretch to say that Richardson invented them. That might not be exactly the right word. But Richardson is the guy who kind of came up with this idea that we should be able to divide the world up into little boxes or little grid points and apply the 7 primitive equations and solve it. Now, in fact, he was way off as to how exactly that was going to work. But he had the idea that you could use a computer to do this. And he made descriptions and poems. He was a strange guy. In general, actually, he's a fascinating guy in the history of meteorology, but he did things like write poems about the viscosity of the atmosphere and so on. He's an odd guy. But he kind of came up with this description of how, like, he could use computers to make forecasts of the weather all around the world. Now, in his time, the word computer meant dude, okay? A computer was a person. And you can kind of see, if you look at the picture here, you know, there were like little people there behind each of these grid. He pictured it being like a big domed building, and there would be people behind there doing the calculations, and he would be like orchestrating how they were all doing their calculations. Well, of course, he had no idea about mechanical computers that became electronic computers, and this was all done 100 years ago. But anyway, it was kind of an interesting and fascinating little insight into how this stuff was invented and so on. Obviously, he was off in all kinds of important ways. And actually, some of the ways in which he's off are important insights into other criteria in the atmosphere and so on, which we are not going to get into. But I thought this was kind of a fun little thing to read about. In the meantime, we're going to talk about the main theme for today's lecture, which is this business of ensembles and ensemble modeling. And I wish that we had a great reading to help you about this. And I'll see if I can find something, but at the present time, I don't have something great to help you understand this concept. So let me pick through this a little bit carefully using a number of slides that I use, actually some of these in other courses and so on. Everything that I have shown you so far in the model, in this lecture, has been an example of what we call deterministic modeling. Deterministic modeling is when you use one model, and like as in one numerical model, one computer program or whatever, and you use this model run, and you use the output of the model as your forecast. Whether that means like as in you've run your model for 72 hours out in the future to make a 3-day forecast, or whether you've run one model out to the future to see what 100 years from now the climate is like. But the emphasis here is on the model, a model. We are assuming that there is one model here, and that model is telling us what to expect. That is deterministic modeling, but deterministic modeling has some hidden assumptions in there. I mean, we know that there are going to be problems with the initial conditions that we give this model, and for that matter, there are lots of models to choose from. In the case of numerical weather prediction, there are models that are used in the United States, there are models that are used at different universities, there are models that are used in other countries. There are a lot of these different computer programs that are modeling the weather, and in the case of climate, lots of different research teams and federal agencies and so on have their own computer models that are simulating climate. See, the answer that we are getting is, as far as our simulations, whether it's 72 hours out in the future or 100 years out in the future, is to some extent a function of what we chose for our model. I know that if I ran a different model, or if I ran the same model but with slightly different initial conditions, or frankly with slightly different boundary conditions, I would get a different forecast. This is a real limitation in deterministic modeling. If I'm only running one model, to some extent the answer that I get depends on which model I chose. That's kind of a hidden assumption in all of this. When I run the model, I need to understand that to some extent the answer I got depended on the choices I made. Okay? If I want to simulate the forecast for 72 hours in the future, and I'm using I'll throw a model out, the GFS model. That's one of the Global Forecast System model. I'll get a slight, well, maybe slightly, maybe very different answer than if I had used a different model, like another model is called the ECMWF model, the European Center for Medium Range Weather Forecasts model. maybe the answers would be very different. More importantly, I have no idea how I would even tell. That's why ensemble modeling is a better idea. It's a different and it's a better strategy for working with numerical models. But this word ensemble can be a very tricky word. If you ask Google to define ensemble, it's going to tell you it's a group of musicians, actors, or dancers who perform together, which sounds terribly wrong, except it's not actually not so far off. Let me put a pin on that for a second here. Now, definition 2, a group of items viewed as a whole rather than individually. We're going to run a bunch of models and then not look at them individually, look at them as a group. What is the group telling us? In the same sort of way, I like this definition 1 here. Think of these models as like each individual one, the right word is member, each member of the ensemble is itself a model, and all of them are performing together. We are running a group of models, all of which are different, to find out something collectively about the atmosphere in this case. In ensemble modeling, in the context of numerical weather prediction or climate modeling, in ensemble modeling there are many, possibly very many, numerical models all producing forecasts for the same point in time in the future. Wait a minute, I thought you said, Dr. Shragi, that all these running a model is a nightmare and it takes a supercomputer. Yes, it does. Does that mean that, like, oh my gosh, if we're going to run many, possibly very many copies of the model, it's going to take possibly very many supercomputers? Yes, it does. This is not for the faint of heart. Okay, this is a very large amount of computation here. Each member of the ensemble itself is a numerical model, whether it's a numerical weather prediction model to make a forecast for 72 hours from now, or a climate model to make a forecast for 100 years from now. Each member is itself a model, and each of them is going to be producing, presumably, a different forecast. Which sounds like a nightmare. Which sounds like exactly the wrong thing has happened. I mean, so now instead of having one model and I can look at its output and decide what it means, I now have, let's say, 20 models, and they all have different answers as to what the weather's going to be like 72 hours from now? Yes. Oh my gosh, that sounds like a disaster. But it's actually a hugely beneficial strategy because it's going to help us not only understand what turns out to be the most likely outcome, but it's going to tell us something about what the range of outcomes can be. With 20 model simulations running that are all equivalent in terms of equally likely to be true, we're going to find out that there's a range of possible outcomes. Some of the models will have, let's say we're running about 100 years into the future. Some of the models will have more global warming, some will have less. There'll be kind of a cluster of ones that are, well, there might be anyway, a cluster of them near the middle. What is the most likely outcome? What is the range of possible outcomes? What a powerful tool, but man, what a what a mess to think about. Glossary of Meteorology is a tool that we love in climate sciences and meteorology and so on. And the Glossary of Meteorology from the American Meteorological Organization, American Meteorological Society, tells us that ensemble forecasting it's a set of different forecasts that are all valid at the same forecast time. The difference between these forecasts provides information about the probability distribution of the predicted variables. You're going to make a whole bunch of forecasts that are all using those climate models or those numerical weather prediction models. Let's use numerical weather prediction. We're going to make a whole bunch of forecasts for 72 hours from now. And then we're going to look at the distribution, the probability distribution of what the outcome is. They'll all have come up with slightly different ideas about what the high temperature 72 hours from now will be in Omaha. But now we have some sense of what the range is and what's the most likely outcome and so on. What a powerful tool. It's too bad it takes like just a back-breaking amount of computer science to make it happen. Let's focus on the weather first. Let's talk about ensemble modeling in the context of numerical weather prediction, because in some ways that's the easier one to think about. Ensemble modeling of weather. Now, remember, weather forecasting using numerical weather prediction, we've shown already, is an initial value problem. We need to have effectively perfect initial conditions that we give to the model as input in order to have a valid forecast for 72 hours from now, or 4 days from now, or whatever. Because, I mean, the physics of the atmosphere is well known. Those 7 primitive equations, that's not the problem here. So what we learn, thanks to math PhDs out there, is that the way the atmosphere is going to change turns out over the next 3 days, 4 days, 5 days, or whatever, how the atmosphere is going to change, what's going to happen to the jet streams, what's going to happen to these storm systems, and so on, is very sensitively dependent on knowing our initial conditions, the model that we are using as input. And that is impossible to get. We don't have perfect information. We barely have adequate information over land, over developed countries that launch weather balloons and so on. Don't even get me started over the third world. Don't even get me started over the oceans. We don't have perfect initial conditions. But this turns out to be a problem we can get a handle on using ensemble modeling if you have enough computer power to do it. We could run a large number of weather models, an ensemble of these models, in order to get a sense of what is the range of possible answers we could be getting. So, for example, let's say we want to make a forecast. And what we're going to do is we're going to collect all the observations from today. And we're going to load them up as input into the model, just exactly as they came in from the surface weather stations, the upper air observations, whatever else is out there. And we're going to call that run 1, kind of like a control run or whatever. It's not exactly a control run. Let's call it run 1. Before we actually see how we would do things different for other members of the model, let's actually look at what some of that information that went into the model looks like. So, like, for example, one of the pieces of information that went into our first simulation, run 1, was the temperature in Omaha at this hour. Let's say that the weather station in Omaha at Epley Airfield reported 50 degrees Fahrenheit. Well, think about all the possible sources of error in that observation. From the equipment is out of calibration, to we round the observations to the nearest degree. I mean, the temperature could be 49.5, or it could be 50.4, or whatever. To, yes, but it's a little warmer near the airport than it is over the city. To, I mean, how representative is this location? There's any number of sources of errors. 50 degrees Fahrenheit is just an estimate of the temperature here. It might be a good estimate, it might be a crappy estimate, but it is just an estimate. In fact, because that's realistically just an estimate of the temperature, it could very well be that that's not the right temperature. In fact, it isn't the right temperature in Omaha right now. And so guess what? Run 1 is doomed to fail. It was born to die. Okay? Run 1 cannot give us the correct forecast far enough into the future. Well, far into the future, because we already have the wrong initial conditions in the model. Okay? No matter what the right temperature is in Omaha, it's probably not exactly 50.000 degrees. But maybe that's not terribly important. Maybe the forecast for what's going to happen, at least for the next few days, is not terribly sensitive to the temperature in Omaha right now. For example, maybe we could test that by saying, let's not plug in 50 degrees for the temperature in Omaha. Let's plug in 49.6 degrees Fahrenheit. Because here's the deal, we can't tell the difference. The truth of the matter is, if the real temperature in Omaha right now is 50, or if the real temperature in Omaha right now is 49.6, guess how it's coding up as an observation from the surface station? It's coding up as 50. We don't really know the difference. Now sometimes, so that's consistent. It is intellectually consistent to say the temperature right now could very well be 49.6 degrees in Omaha, or it could be 50 degrees. So why not run the model with 49.6 and see what happens? Okay, we could adjust it slightly. In practice, it's randomly. We just make small changes to the temperature. Maybe that tiny difference in the temperature between 50 and 49.6 turns out to make a forecast wrong. Well, it does make the forecast wrong. The question is how far in the future? Will that change what the high temperature today in Omaha is? Probably not. Will that change the forecast for tomorrow? Maybe. Will that change the forecast for 2 weeks from now? Definitely. Somehow or other, we have to figure out how big these range are. So what we're going to do is we're going to take a second run of the model in which we have slightly adjusted those initial conditions. Based on like small random changes, we're going to just let the computer make random changes, move the temperature up in Omaha by 0.4 of a degree, move the temperature down by 0.2 degrees in Lincoln. In fact, there's a whole branch of computer science and analytic mathematics that knows good ways to do this. Okay? But you're kind of getting a sense of it. We're just going to say, hey, you know what? If this was what the real temperatures were in these locations, we wouldn't be able to tell the difference between what actually came in the observations. And so we'll have a run. Now, if we ran this run out 20 days, these two runs would be very different. If we ran those simulations out 20 minutes, we wouldn't see the difference at all. The tiny little difference in the temperature doesn't, that we're feeding as initial conditions won't make a difference in the forecast for 20 minutes from now. But it'll be the difference between a busted forecast and a right forecast, or more likely two different busted forecasts 20 days from now. And then let's just keep looking at them. I mean, these two runs might turn out to be more or less the same for a short period of time, like maybe a few hours, a few days, or whatever, or they might be very different. So let's just keep repeating this process. Let's not just have 2 runs, let's do it 20 times. Let's have 20 different supercomputers running the same model, but with 20 slightly different sets of initial conditions. Each one of those models is a member of an ensemble of models that started off with initial conditions that were effectively equivalent. But they weren't the same. They were all slightly different just by little random changes. But from the point of view of what we would know about the atmosphere in terms of our error bars and so on, they're all equivalent. Alright, we have all these different runs, and now we have 20 different forecasts for our 48-hour forecast or whatever. But that's not a bad thing, that's kind of a good thing, right? Because the 20 different forecasts are kind of giving us a sense of, look, this is 20 different ways the atmosphere could play out over the next 2 days. And we can take a look at the one that was coldest versus the one that was warmest, so we can get a sense of what the range of possible outcomes is. Or we can look at the wettest one versus the driest one and see what the range of possible precipitation is. And we can see how they're, most of them were what was the most likely scenario. Oh man, what a powerful tool! But man, figuring out how to interpret that's going to be really hard. We'll have to do that in part 3 of the lecture. In the meantime, let's answer a couple quick questions about what we just saw. Question 6. At the same resolution and with the same time step, ensemble modeling of the atmosphere is more computationally intensive than deterministic modeling of the atmosphere would be. And notice I underlined the word more. We can go ahead and assume that's the only word that might be wrong here. Is that more or less? So true or false? Is this statement true or false? Make a choice from those 2 options and get a little feedback before you move on to question 7.